online. First, we're gonna get welcome to Jonathan Osorio. He is doctor in medical physicist from Med Austron Center, Viena, Austria. Entonces, damos la bienvenida al doctor Jonathan Osorio, doctorado en física médica del Med Austron Center de Austria, de Viena, en Austria. Él nos va a acompañar con la charla An Overview of Light Ion Beam Therapy from Beth Block to Chondrosarcoma. Okay, welcome, Jonathan. Thank you very much for being with us.
Sí, muy buenos días para ustedes. ¿Cómo me confirman si me escuchan?
Sí, señor, se le escucha perfectamente.
No. Entonces, déjame compartir la pantalla. Sí,
Listo, perfecto. Ya se está conectando su pantalla. Ya le estamos viendo.
ok, perfecto. Bueno, sí. De nuevo, muy buenos días a todos ustedes. Agradezco muchísimo la invitación a esta pequeña charla sobre, es un overview básicamente de lo que se hace en Particle Therapy. No sé si desean que sea en inglés, en español, alguna. Me disculparán porque todas las slides están en inglés, pero pues.
Profesor Jonathan, si no tiene ningún inconveniente, sí preferiríamos que lo hiciera en inglés para las personas que de pronto están online y no hablan español.
Okay, perfect. Then there's no problem. So once again, thank you so much for this invitation to this event. And I'm Jonathan Osorio. I was a physics student there in the National University of Colombia. Then I did the master in medical physics, and then I got my PhD in physics in Italy. And basically, I will have the pleasure to show you really, it's an overview, basically. This is a journey about what is the particle therapy. Currently, I'm a medical physicist here at Metallstrom in Austria, which is a center that provides particle therapy with proton and carbon ions. So before, I have to give a super special thanks to all the community in particle therapy that are providing the knowledge and the know-how how to bring this kind of new therapy. Well, at least not so many new therapy. It's already around 20 years that this therapy is ongoing. But it's a new possibility, a new way how to try to reach, even though so quite difficult tumors and quite radio-resistant tumors. So this is a special thanks to all the people that is working in this field. So this is an outline what we are going to have a look today. So basically, what's light ion beam therapy? I'm talking now about the light ion therapy because I want also to talk about the proton and carbons, which are currently used in patients. There are some trials, some studies about the helium and some IV ions, but for the moment, what is used in the community is only proton and carbon ions. We have a quick look, just a refresh about the beta block formula. Then differences between particle therapy and proton and carbons. Also a little bit of an overview about the machines that provides this kind of possibility of therapy, peak delivery system, TPS, clinical indications, a few words about the quality assurance or QA, and just a quick overview about the facilities worldwide. Then, what is light ion beam therapy? So basically, it's a type of external radiotherapy, but instead of use photons, say 6 MeV or 18 MeV, we use is protons or carbon ions. But why is so fancy, basically? Because it has a really particular effect, and it's due to the physics, and it's the fact that the high amount of energy it can be localized in a certain depth inside of the patient or in the phantom or any medium that we are irradiating, and we can control this depth. So we can move this high amount of energy delivered to the medium in a particular depth, and it's not like the photon that we have is really driven by linear coefficient of attenuation, and we need to increase the energy in order to get a little bit more high energy given to the medium, but this is quite shallow. It's around centimeters. Here we can really control this depth, and we'll see why in the practical terms. So this is the case, a real case actually, a real case of a young lady that has an earring sarcoma, where you might see the difference between the proton cameras. Here, all the details, all the fractionation, all the scheme, but basically here you can see the PTV, so the planning target volume. So basically where we want to give all the external radiotherapy, and if you use a photon beam plan, you need to make an arc, or you need to try to spread the dose around the healthy tissues in order to try to minimize the impact on the healthy tissues, and then you give the prescribed dose to the target volume. But in protons, basically, the advantage of the particle therapy is that you don't need to spread the secondary dose in a healthy tissue. You basically use 3 posterior beams, and then you have the same coverage, or sometimes even better than beam. So basically, the advantage, or one of the huge advantages of the particle therapy, is the capability to spare the healthy tissue organ at risk. And you can see this more clearly here. So basically, the colors is self-demonstrative how much you can spare about the dose. So basically, violet is 20 grays less using protons. Red is 15 grays less using protons, and 10 grays using protons. And you just only can change the type of particles. Another quick example, one of the major benefits is of the pediatric patients. So, for example, this one is a tiny baby which has a quite bad prognosis. And then in this particular case, you might see here on the top the photon plan, where you need to pass through them the temporal lobe, the mandibula. There is a lot of possibilities that that for kids is quite difficult and quite relevant to spare the organs, because they are babies and they grow up, and then might influence some side effects. So lack of growing of the tissue, all the stuff. You might see here also that the dashed lines are the proton plan, and here you can see that you spare a lot the temporal lobe and also the mandibula. So basically here you can clearly see on the in the deviation that how much you can spare. You can see here the difference between the proton and photon plan. So let's go back a little bit on the basic stuff, the physics. So here you have like a pencil beam with photons, and then you have here protons, and you might see clearly that the difference in the amount of ionizations inside of the medium is quite remarkable. And basically, this is coming purely for the physics. So this is a really all the slides, but it's coming from one of the best courses that I had in my life. So that was the course of Clases de Física Nuclear that was given by Professor Fernando Castancho in the National University, and explained clearly, really simple, the difference between the physics between photons and charged particles. So basically here, if you have a material, a medium, whatever, and then you have a certain beam, photon beam, basically the interaction inside of the beam, so the photoelectric effect, quantum effect, pair production effect, can be easily described by the linear coefficient of attenuation. And basically the physics says it's really simple. If you have a photon beam with a certain energy here, the intensity of the beam is reduced inside of the medium, but at the end, the energy that you get out of the material is exactly the same as you have at the beginning. So basically, if you have 6 MeV photons coming into the material, then you get 6 MeV photons getting out of the material. But if you have 100 photons, let's say, coming into the material, then you might get like 20 photons getting out of the material. Instead of the particles, you can call it charged particles, whatever, then the story is tiny different. Oh, sorry. The story is tiny difference. So you have a beam that has certain intensity in the beam. Intensity, the points that the beam is also attenuated, it's also reduced, but the incoming energy is not the same as the outcome energy. So basically you have an initial energy, and then inside of the medium, all the particles, or the majority of the particles, release the energy inside of the medium, and then you have here a distribution of the energy deposit given inside of the material, and this is really relevant because with the energy you can localize where do you want to put the dose, and we are going to talk about this more clearly. So this is a funny GIF that basically describes what is happening. So you have a really localized beamlet or localized beam that is able to provide a lot of, release a lot of energy inside of that medium. And this is basically described by the Bethe block formula. So it's a relatively complex formula, let's say, but we can clearly see here in this fancy row. So basically, it depends on two main things for the purpose of this talk that is really informative. One is if you have super high energy, you have a beam with the super high energy, what is happening is that let's assume that the particle goes through so fast that the atoms and molecules inside of the medium doesn't have time to react, and then the electrons are not ejected, they are not ionized because they don't have enough time, let's say, they don't have enough space for interaction, and they need to have the main property that we want, that is to release energy in the middle and then extract these electrons to make ionization. But if the charge of the particle and also the velocity of the particle, the speed of the particle, so basically the energy of the particles is slow enough, then they have time that the field of the beam interact with the electrons of the medium, and then you can get out of these electrons, and then you get the main goal of the radiotherapy, that it's mechanization inside of the medium, so provide energy inside of the medium. And basically, this is described by the so old and good old friend, the Bethe block formula. So basically, these are the characteristics of the medium. But what matters at the end is what is the speed of the particle and what is the charge of the particles that are irradiating the medium. So this is more or less the really good summary about what exactly is inside. So if you change the energy, as you might see here, this is a carbon ion beam. You might have, if you want to penetrate, so you go deeper, you need to increase the energy of your incident beam. So the carbon has to have high energy in order to try to get 25 centimeters. But what it matters and what is really relevant here is that all this area, all the plateau area, you are releasing low amount of energy because your particle doesn't have time to interact and make ionization inside of the medium. But so slowly, it's getting losing energy. And then at the end, at the Bragg peak, the famous Bragg peak, then we have the tiny but really important particularity on really physics behind, and is that due to the stopping power, the incident beam is releasing the highest amount of energy in the medium, and this is around the size of 10 microns. And particularly 10 microns has the size of the diameter of the DNA. So basically, this is super nice and super well-desired feature because you can destroy, you can really have a high probability that you are breaking the double strand brains inside of the DNA. So this is again to show you that if you have different particle types, so different ions, neon, oxygen, carbon, protons, then if you want to reach a certain depth, like 27 centimeters, more or less, crossing through a normal patient, this more or less the size of the domain, then you need to increase the energy if you want to use different ions. Then, as I already said, the dose given into the medium is basically described by the stopping power. So basically, the energy that you are releasing in the medium, the fluence of the medium, and the density of the medium, and some correction factors. Now, what is the difference between protons and carbons? Basically, they are driven by the physics and the biology. Regarding the physics, this is really quite simple, but really relevant stuff. So for protons, as they are like light ion particles, here you might see in blue that they have a high scatter property. So you can bring the beam, the beam inside of the medium, but before that you need to cross the so-called the nozzle of the accelerator, and then you need to release a certain air gap, then you need to pass that, and then you get to the medium. But then you can increase the full width and maximum. So basically your beam is start to get increasing, and then this might be an issue regarding the penumbra of the beam. Instead of carbons, they are heavy ions. relative to the protons, then they don't have too much scattering. You might see here that basically they start to scatter when they start to enter in the medium. In this case, it's water. This is a really important feature regarding how to spread the organelle beads, because you have less penumbra in your PTV, and then you can focus better the dose inside of the medium. Now we need to give a few words about what is LED, because the LED basically is the energy transfer, which is quite similar and quite misconfused with the stopping power, but they are not the same. Basically, the stopping power, except not that it didn't include all the effect of relative energy loss. So basically, it's the loss of the energy from the point of the beam, and the LED is the energy gain inside of the medium, but not from the point of the view of the beam, but inside from the point of the view of the medium. So basically, the difference between the LED and the stopping power is that the local energy deposition it's only given on the LED, and the stopping power is the total energy lost by the particle, as I mentioned, with respect to the point of view of the incident beam. And in the particular case, for particle therapy, we have a high LED that is given in a non-uniform pattern. So basically, it's a really focused, really concentrate energy release, energy inside of the medium. Instead, with photons, we have usually broad beams, or we have the MLC, or we have collimated beams. Then you have to distribute the energy deposit given it into the medium in a more or less uniform pattern. Of course, here assuming that we have a uniform phantom. So from biological point of view, low LED means like 20 Kelvin per micron. So this is far away from the distance of the DNA. Remember that we have around 10 microns of diameter. Medium LED is around to release from 20 to 100 Kelvin per micron. So it's roughly close to the DNA diameter. But then if you have super high LED, then like 1000 Kelvin per micron, then you have a high density of ionizations in a really tiny distance. And this is really an advantage if we want to make a damage inside of the tumor cells. And here you can see quickly alpha particles, carbon ion tracks in different scales, and you can see the amount of density of the ionization. So in summary, we have the super nice distribution that we have low energy given to the medium, low LED in the entrance of the beam, and then high LED, but I can control this step, and basically I can control where I want to give this high amount of energy. So basically, it means that, in summary, you know that all this story belongs to the radiolysis of water, and then for photon beams, we have indirect predominant effects, so basically our secondary particles that try to have a probability to try to break one strand breaks, or maybe two, one here, one there. But for particle, they have a direct effect. So basically, they are super short, and they can break more than one of these bounds here. And this is given by the radiolysis. Sorry, I forgot the name in English. But basically, I guess you are already here about this story about the radiolysis and biological effects. Then I give it for the other conferences. Again, this is a picture that shows a microscopic level. How does it work? I hope that you can see. I have this video about that. Let me see if you are able to see it. Please confirm that you are seeing a video. Can you see a video there? Hello. Hello.
No se ve el video, pero ya intentaste y no se ve.
No se ve.
Sí, no se ve el video correr.
Let's give it a shot. Share. Okay. Now it's better. So basically here, it's in vivo bioluminescence irradiation of stem cells. And here you can see basically the local damage, high density damage. Don't ask me about the detail because I'm not a biobiologist or biologist to know exactly which kind of substances use it, but basically you can see here in the microscope when you get these highly density ionization, and basically this is a lethal damage inside the tumor. You can see here even damage inside of the nucleus of the cell. Let me give a try. Then the other one, which is quite fancy. Screen share stopped. Okay, give a second. I show you another one. Fancy. Give me a second, please. Stress. Zoom is not the best. Make the conference. And then okay. Oh, no. Okay, that's gonna be tricky to show the videos. The scope of the presentation. Okay, I hope that you're looking at the presentation. So basically, the video is also showing how this is generated in vivo in time. So basically, here you can see the damage inside of the inside of the beam, inside of the cell. Sorry. So in summary, why is better or what is more advantage to use ions for the protons? Because they are more effective to make a damage to the biological level. So basically, they are more effective in order to kill the cells. Protons are almost similar in terms of biological effects with respect to the photons were. Then this is really a super quick summary about why particle therapies, why carbons are, let's say, better than protons. Each one of them has their pros and cons. And now let's talk about a little bit of the machines, a little bit of because we are mechanical physics, we are a broad public, and the purpose of this is to make an overview. So basically, what is the beam? So basically, a beam is not only one electron or one proton or one carbon ion or one helium. It's a bunch of particles that are traveling into the accelerator. And basically, the way how we accelerate this is basically using our RF cavity, radio frequency cavities, which is basically as simple as that, it's as simple as like a capacitor. So basically, you have electric field in front of you with the opposite charge of your beam, and then when this is approaching to one of these these plates, let's say, then they change the polarity and they get a kicks inside of the cavity, and this gets a kick every time that they pass through the one of the sectors of the cavity, and then you can increase the energy of the beam until the proper energy that we were talking about is around 400 MEPS for carbons and 250 MEPS for protons. So of course, this is a really simplistic way how to say it, because there is a really science behind the design of the RF cavities. There are superconducting RF cavities, and there are a lot of techniques, a lot of high electronics, how to create it. And this is coming basically from facility like CERN or GSI. Then once you're able to accelerate the beam inside of the accelerator, then you need to control the beam, right? Then therefore you might need really simple formula is the Lorentz formula. And basically inside of any particle therapy facility, you might end up to find always roughly 3 or 4 kind of magnets. So basically, we are talking about the Lorentz force, and then you need a magnetic field in order to control the beam. So basically, there are the bending magnets that are the guys who control the trajectory of the beam. Then you might have quadrupoles that, as you might see, is a magnet with 4 poles. And basically, this is to control the dispersion side of the beam, because you have a bunch of particles and they try to go up and try to escape, because basically everything is ready with the control. And you have sextuple that they are making like a fine tuning on this spreading of the beam, let's say, some moment in dispersion. Independently of the type of accelerator, all of them has, as I mentioned, magnets, but there are mainly 2 kind of currently used in therapy of accelerators. One are the cyclotrons, and the other are the synchrotrons. Basically, the main difference between them is one, the size, because this is quite big size, we'll see later. And this is the synchrotron, which is quite not so big, like 2 meters diameter. And the main difference here, you have a constant magnetic field, and here you have a variable magnetic field. So basically in this, it's like to try to control particles in a circular motion with the high energy. So basically for keeping that control, keep the particle inside of the ring. So basically in the circular motion, you need to increase the magnetic field. In this case, you don't have a permanent radius, you have as a permanent magnetic field, and you increase the energy, increasing the radius of the particle moving. So this is a GIF that shows you how does it work. So basically you have an alternative, right? Your air cavity is just an alternative gap inside of the permanent magnetic field, and then you have a different trajectories, and that your particles start to gain energy turn by turn. Currently, it's only available for protons. You can tune the beam intensity. It's quite hard reliable because all the IBM machines are not having any retirement for any of the companies that are making accelerators. But basically, this is the one, the most famous manufacturer of the cyclotrons. They have some drawbacks. For example, there are no energy variation, and also you are not allowed, well, not allowed, but they're not designed yet, at least in the market. They use for heavy ions because technically there are so many complications. This is some photos about these cyclotrons. Of course, the previous slides are the really simplification because this gap shows the place where the particle has an acceleration. This is optimized in such a way that the particle really getting high energy in a really short diameter. And now there are the places like where I am, that is mid-ocean, where we have the cyclotron type accelerator, which basically is a fixed radius. And we have a magnetic field that is changing when I want to increase the energy of the particle. So basically, if I want to keep this force and this particle move at high energy faster and faster and faster, but then I need to increase the magnetic field in order to keep the force in it. This is another synchrotron that I also was working a long time ago. That is basically the twin brother, twin sister of this facility. This canal. This is in Italy. And as you might see with this photo, it's approximately 30 meters diameter. So you need a big space to provide these guys. And the good thing about these machines is that you can change the energy quite quickly. In the cyclotron, you cannot change the energy. You need to put a mechanical degradator of the energy in order to control the depth or control the energy of the beam. The really nice things about these machines is that they are suitable for protons and ion treatments. It's not only carbon, helium, so you can put whatever that belongs to the capability of the magnetic field that keeps the particle inside the trajectory. But so you can put many ions in the cyclotron, you cannot. The drawback is a big machine. You need an injector system, and it's quite complex operation because it's like to be the director of the orchestra. You need to really control the dipole, the quadrupole, the sextupole, the ref cavity. You need to control many things at the same time, and all of them has to work properly in order to get inside the turret. I have a nice simulation, but I don't know if I will be able to show you. Hopefully, yes. Can we just let's give a try? We can do that. Otherwise, we will skip that part. Let's see if we can do something. Give me a second, please. If I'm trying to make this thing working. No, you cannot. You can still lay off. Okay, no, that's a pity, but okay. That's the problem of the online stuff. But okay, forget about that part. I want to show you how behaves the beam inside of the cyclotron and see how difficult it is to control that the beam has certain emittance. So basically the size of the beam inside and inside of the cyclotron. And this is basically the charm of this kind of machines, that you need to really tune carefully all the magnets, all the earth cavities, all diagnostic elements in order to don't lose your beam and basically to provide the beam until to the patient. And maybe one of the basic questions is why these machines are so big. And basically, the answer to that is basically the magnetic field. Then, few words about physics. So, why so big? Why the carbon ion countries, the proton countries are so big? But basically, because we can control the beam only using the Lorentz force. So we bend the beam in one direction and another direction purely with the Lorentz force. We accelerate the beam with the ref cavities, and that's it basically with electric field. So here, if you make a little bit of gymnastic, really, really simple gymnastic, you end up to the fact that the energy that you want to give to your particle is strongly correlated to the magnetic field that is available in your system, and rho, that is the bending radius, is proportional to the energy. So that means that if you want to make a machine that is able to bend the beam, to control the beam, to put it inside of the cyclotron, then basically, if you have if you want to have a smaller radius, a small bending radius, you need to have a quite high magnetic field. And this property, the B rho, the magnetic rigidity, in order to get the energy that the particle beam, either proton or carbon, are able to penetrate at least at 30 centimeter depth, then you get basically these constant numbers, around 3 for the magnetic rigidity for proton and around 6 for carbon ions. So it might not meaning too much this number, but believe me, it's a really reason why these machines are so big. This is a photo of the carbon ion gantry at Heidelberg, and this part here is only the last bending dipole. So basically, this is the room, this is the end. So basically, this part that you are seeing here, I hope that you are looking my mouse, because I'm pointing there. But okay, let's assume that yes. If not, please confirm. And basically, this is the photo of the treatment room. So all these big things you can see here, a small guy, that you can have an idea about the pressure or how big can be this problem.
Te confirmo, todo está perfecto.
Thanks. You can see also here, you can see here the size of this kind of machine. So basically, this is the size of a normal guy, and this last bending man is like this. So the B rho is 6.64, and then with the normal conducting magnet, so basically with the magnet that we have in the power supply or stuff that we know from kids, that we have just a coil, then we end up to the bending radius of 3.67 meters, so roughly 3.5 meters, because we cannot get magnetic fields higher than 1.8 Tesla if you not end up to the saturation effects and also the high hysteresis effect. This is a simulation that I did my PhD thesis about the particle tracking inside of this kind of magnets. And basically, one of the things, okay, this is also me, to try to give an idea how big are this kind of stuff. This is the gantry that we have here at Medalson. This is only proton gantry, but even like that is even big. And this is a tiny simulation that shows you, in particular for this last bending magnet, how much power do you need for this machine. So basically, we need to have a ramping current of 500 or approximately 500 amps per second in order to get a magnetic field rate of 0.4 Tesla per second. And at the end, you get up to each one of these magnets, it consumes 2,300 amps. So which is a huge amount of energy that needs to be provided in order to get a beam that is crossing only the field of view that is around 20 by 20. And here you see how much this is the part of the yoke. So basically the part of the iron that needs to be in order to control the lines of the magnetic flux in order to get here a really, really homogeneous magnetic field, because any tiny variations in the magnetic field will get to the particle that is getting in a different part of the patient and it's going exactly on the wall. So imagine if I have a chondrosarcoma and then I need to spare the brain stem. If the beam is not getting exactly what I want, then nothing to do. Then I need to have a super high quality in the magnetic field. This is just a taste on the machines. Now let's go to the nozzle of the machine. What is the nozzle? Basically, the last part of the, let's show it here, was too much. Basically, now we are talking about here. This last part of the machine, basically, this is the monitor unit detectors. So the initial chamber that we need to use in order to how to get the beam inside of the patient at the shape of the PTV. So basically, the old-fashioned way, the passive beam shaping, this is the passive scatter devices, which basically it comes from copy the old-fashioned idea to scatter the beam inside of electron accelerator beam, so the Linux, because basically you have a scatter, and then you can have your broad beam, and then you have your MLC, and then you make the conformation of the beam in order to get to the PTV. This is quite really old-fashioned, and the new facilities, almost no one of them are using this kind of techniques because it has a drawback that you have too many elements on the beam, and basically what is happening is that you can generate a lot of neutrons inside of the patient, and then that means that we can really adapt to the situation that you need to provide a personalized collimators in order to treat each one of the patients. So you have a lot of waste, a lot of say waste inside or inside of your facility only for treat each one of the patients. So it doesn't make too much sense. And also the secondaries also contributes here to the proximal part of the patient, and that is not the best thing to do. Anyhow, the old accelerator, the old cyclotrons, still working with this technology. That was the first approach on this, like 15, 20 years old. Way how to shape the beam in order to get into the patient. This is a photo of the eye treatment inside the PSI at Switzerland, and you might see all the elements that you need to cross in order to get really a tiny beam. The PSI is based on cyclotron basis. The one that is most common use since like 10 years or more, it's the active scanning system, which is like the old-fashioned TV. So basically you have two different finite dipoles, which are scanning vertically and horizontally the beam, and then you can control the energies or the depth of the beam with your accelerator. And in order to be super extra clear, that you can see this. Oh, this one. Oh, this is work. No, it's really good. But this one I really have to show you because otherwise you will not understand my idea. Give me just a second, please. I will share. Second, please. Then I will share this with you guys. So basically, as I was mentioning it, basically this is the tumor, this is the PTV, and then you cut the tumor like in slices. So this is one energy, and you scan it in the transversal plane. You see that you can go through with the beam, and this is like the old-fashioned TVs. It's not that like the newer TVs with the LED or whatever. It's just the beam that is scanning and making the shape of the PTV. So the advantage of this kind of mix. Let me go back to the presentation. Is the fact that you avoid the neutrons. You don't have secondary particles there. I can do that. Okay. See this work. Okay, but basically I was supposed to show you. So this. Sorry if I take more time that I should take it, but the limit is worth it to have a look at these things because it's not so frequent that we are able to see this kind of videos. Yes. Share. Yes, you are looking at my screen now. Yes. Then share. So basically, this is also PSI in Switzerland. This is a proton beam. And this is the way how in real life you have a scintillator material, and then you can see how the beam, you can really control the depth of your beam. And then if you scan it in the transversal plane, then you can draw in 3D the shape of your tumor, the shape of your PTV, and then you can have really control where the energy is given into the tumor and not outside the tumor. Basically, you have just to have a nice a nice control system of X-ray or in vivo, not in vivo dosimetry, no, but it's just a tracking system and tracking cameras, and then you can control where you're being. And basically, that is how this technology works. So high control in the beam energy and also in the position of the beam. Okay, thank you for the simulation. Let's go back to the presentation. Sorry for this. Then, okay, we come back. So basically, the video that you already saw is the video that is running here. And this is basically the simulation of that beam. So as you were able to see, then we can control the depth of the beam just by the energy that the noise selector is providing me. And then the scattering is just pure physics. And then we come back to the one of the major problems that we have here, and is the organ motion, which restrict a little bit the kind of tumor that we can treat with this therapy. But nowadays it's getting better and better because we have better tracking system and control system inside the machines. So basically, this is a tiny simulation that I did just to put some Gaussians one after the other, because you can simulate the pencil beam like a Gaussians, and if you have in the proper spacing, then you have quite flat beam. If you have carbon, then you have this spinograph even less. But let's assume this is proton, for example, and then you have a super nice profile. But if you just tiny move, like you vary the position of the beam like by 10% of the intended position, then by superposition of these beamlets, then you get this kind of shapes, and then you have a non-uniform dose, which is the thing that all makeup physicists we hate, that is to have not uniform, at least this for dosimetry, to have something really clear. Then you might have this hotspot, and then maybe that hotspot can end up to the chiasm or brainstem, which is the nightmare. So basically, we need to deal with the motion. We define this so-called TRB. We can define larger areas like the PTV. We can implement a tracking system to control in real time where is the tumor, and then make a step and shoot, but with the beam. Then we really need to be careful about where to read it. So basically, in the thoracic region, when everything is moving, lungs, liver, all this stuff, that this is quite complex, and we really need to be sure about the robustness of your plans and how to deal with this organ motion. Few words about the treatment planning. So there is one tiny but really relevant detail, and it's the fact that when you make the commissioning of your treatment planning system, you need to be sure that your simulations or your CT images that you put inside of TPS represent first the geometry of your patient, so basically the organ inside of the patient, but also the physics behind the patient. And this is quite given by free because the linear coefficient attenuation of the photon beam is also described by the Hansen unit. So you have for free basically the interaction of the photon, photoelectric, pair production inside of your image. So basically the source of the calibration that you make in your images, that is the Hansfield units, are based on the linear coefficient attenuation, which is basically the physics that you have the interaction of your photon beam inside of the patient, which makes simple, let's say, how to provide this really, really key information, that is the geometry of the patient. In the case of the particle therapy, this doesn't work anymore because we don't have linear coefficient attenuation. Then you need to, let's say, recalibrate your CT in terms of something similar or something that is representative to the image information that you have, because at the end, on the CT, you get the Hounsfield units. But I assume that you know what is the Hounsfield unit, but in case of not, it's the level of rays that you have in your CT images, and this is created basically relative with the water, and this is belonging to the attenuation normalized to the water, to the different materials, tissue, lung, bone, liver, etc., fat. But in the case of particle therapy, you don't have any coefficient attenuation. Then you need to go through, let's say, a detour, or you need to have a nice trick to get that. And then it's basically toward the relative stopping power, because the stopping power is the physics that is describing the interaction of the radiation with the material, with the medium. So in this particular case, what is the trick? Is let's say fancy. So basically, you need to convert the CT numbers in water equivalent path length. So basically, you take the image of the CT and you make a voxelization of this image, and then this is your electron density phantom, and then you need to translate this voxel, so the level of gray, into a treatment voxel. So that means how much energy I will give in that area. So calculate the energy and the number of particles for each voxel, and then this is coming through the relative stopping power. And then that's the trick that here you don't have, I mean, the conversion table or trick or graph is basically this. Here on the x-axis, you have the Hansfield unit, and here you have the stopping power relative to the water. And basically, you need to have the information of each level of gray, how much particles are released in that medium, and how much energy are given by the stopping power, assuming that this gray level is like a density of the medium. So it's a trick that we found in order to be able to make the plans, basically. Then once you overcome this problem, then it comes the fact that, okay, which kind of data do I need to provide to my TPS in order to make the commissioning, the acceptance and the commissioning of my TPS? Then, well, sorry if I didn't say, I guess you already heard about this, but TPS is the treatment planning system. So the software that simulate the geometry of my patient, and then I simulate the interaction of the radiation inside of the patient, and then the doctors, the radiologist wants a certain prescribed dose, center energy in the tumor, and then we as a medical physicists, we are the in charge person to guarantee or to be sure that what the doctor wants to be prescribed inside the tumor, we give it in a real situation, like the patient, like the CT of the patient. So coming back to the TPS commissioning, then we need to provide basically the three things. One is the energy dependency, so basically commissioning data of the depth dose in water, so basically the Bragg peaks. Also the lateral profiles, then in a certain fixed medium. This is the setup that we use here, basically. Those the data that we use here. So basically the transversal profile of the beamlets, right? Basically, yeah, the beamlets, that's it. And also those in absolute conditions, so the reference dosimetry. And this is given not by monitoring it, but the number of particles and function of energy. But we come back later when we see some details about the curing and dosimetry. So few words about the techniques. So in summary, we have two main branches of how to do a plan with a particle therapy. This is the so-called SFUED, so single field optimization, or IMPT, multiple ion. So it's written here, single field uniform dose, or density modulated proton therapy. Okay, I forgot the acronyms, but basically, in order to make the long story short, the SFUD, so the single field uniform dose, basically means that you can have many beams, not too many, like 3, 4 for the particle therapy case, where each one of the beams are uniform distributed. So basically, they provide a uniform dose inside of the PTV. And then what you make later is just to sum up all these beams. You optimize, your optimizer, what it does is, okay, I will keep the uniform of the beam inside of the tumor for all the beams, and I try to get the best arrangement about the number of particles that I need to provide inside of the patient. So basically, here this is a good example. You can see here you have like four beams. So the field one is an ipsilateral coming from posterior part. Then you have here in red more or less a uniform dose. Then you have another one vertex, one lateral vector, lateral vectors, and all of them are uniform. Then if you combine all this distribution, then you have quite homogeneous and nice PTV coverage. Then your DBH will be amazing, but you might end up to a little bit of larger penumbra a little bit of need to find a way how to compromise your optimizer in order to get low dose in the organ service, or at least to complete the clinical goal priority that is given by your oncologist. IMPT is, let's say, nice technique, and the difference basically is the fact that we have the same case, we have the 4 beams, but each one of them, they are not given a uniform dose. This is why it's called intensity modulated prototherapy. Each one of them is given a really irregular dose, but if you combine all of them, then you have your nice deviation, your nice PTV coverage. However, the drawback of this kind of thing is that it is not so much robust regarding possible movements of the patient or possible uncertainties that can be given from different composition of the medium, like to cross air, bone, and this kind of things, and start to be a little too complicated. So basically, we use this kind of technique when there is a certain guarantee that there is not too much movement on the patient, and then you have like a skull base area. We can use this, but depending on the case, it's a pediatric patient, we always use single uniform distribution. So each one of the rings are totally uniform in order to avoid any misalignment, any misposition of the patient will not affect the final result of distribution. Few words about the clinical indication. So for adults, we have all the region in head and neck. It's really welcome to be treated with the particle therapy. Lung cancer is quite challenging, but we also do some lung cancer, liver as well. It's super movable, but we have some techniques in order to try to reduce this kind of lack of robustness. We give the dose very smaller PTB. This is also called PATI technique. Prostate cancer also we treat. Rectal cancer we also, sarcomas also, and pediatric tumors. They are all of indications are welcome. Then this is really critical that the doctors are really doctors or technicians, or the team, the clinical team is really giving a proper drawing and proper prescription about the organal risk in order to try to mitigate the complications. For example, this kind of cases is key that we are able to really give a high grading dose, and you might see here the distance between the PTB and the optical nerves are really like 2 millimeters, and we can reach until gradings until 10 grades per millimeters, something like that. And this is really feasible with carbonite proton beams. But you need to be extra sure about the position of the patient, and the patient is not moving. Another typical case, chordoma, that's the way we call this presentation. Then basically here, you can see quite complex position of the tumor, and you can spare parotis, you can spare temporal lobes, you can make so many things, and we have already with experience, we got some standardized techniques where we can use basically in a head and neck cases, we use almost always 2 CTs, because remember, not all the facilities has a gantry. In carbonite gantry is really, really hard. Only Japanese people have carbonite gantries, and Germany at Heidelberg, we don't have carbonite gantry, we have proton gantry. And then if you want to do different beam entrance, then you need to do different CTs. So you have a normal lie down patient, and we have ipsilateral beam with three angles, and then another CT with the head rotated, and to cover the different another angles. It's like we have a big entry. And then, as you might see, we treat a lot of cases inside of the head because nothing moved too much there,
Disculpe,
basically.
eso,
Yep.
Jonathan, tienes
It's
5
Anita.
minutos.
Fine.
Discúlpeme, sí.
I guess I need 3. Then there are some tricks, some strategies, like we can go for one beam set, basically with three angles, or we can go for 2 beam sets with 2 different immobilizations. There are tricks like we need to avoid dishomogeneity, like to go through the bone and air and then brain tissue, for example. Then we try to avoid to go for ear canal, but there are things that you can avoid this. We can avoid as a structure. This is how it look like this kind of tumors. This is how it looks like in real life. Actually, there was a plan that I did. And here I want to show you quickly the advantage of the carbon and protons. So this is the same plan, same patient treat that we make the simulation with protons. And here we did it with the carbons. And you might see here in the DVH that, or here in this comparison between the two, that basically we can have the same coverage of the PTV, but we spend a lot on the surrounding area. You can see here that here we have a line of isodose. This a little bit shrink, and here is more spread. So basically, you can end up to better grading those here along the short distance, and here it's a little less, and you can see here in this case. Also here, you can spare the nerve roots inside the spinal cord quite easily with the carbons, quite difficult with the protons because of scattering. You might see here. Also here, you can make like miracles in the sense that you can really spare this part of the spinal canal, and you can give this space for a boost, or simultaneous integrated boost treatment. However, there is not always a holy story because, as I mentioned a long time at the beginning of the presentation, there are effects on the radiobiological stuff which may end up to the different response of the dose and different response of the cells depending on the model, the biological model that you are using. We use LEM, that is the use here in Europe. In Japan is used more MKM, which has a different point of view how is modeled the radiobiology inside of the cells, but I guess you will have more presentation about that. And my few words gonna be basically really statistical data from PTCOG, that is the organization that is the Particle Therapy Cooperative Organization Group, which is collecting all the information about all the particle therapy facilities. You might see the types: sarcoma, prostate, the same test that I see. You can see here the relative contribution of each one of them. And basically, oh, no, and I don't have too much time to end up. Sorry, I forgot about the dosimetry. But few words about that. Basically, we don't use the monitor unit. We use the dose for. We use the number of particles that has each one of the beamlets. In the chamber that we need to use, we need to scan the beam. We need to put the insane chamber, your reference chamber, in the plateau region in order to avoid high gradients in the dose. We need to calibrate the machine in a several set of energies because I want to have this is basically this is the calibration that we have here. One of the calibration that I did is basically to calibrate the monitor chambers in terms of number of particles per count, but this depends on the energy. So you have like a polynomial, it's not only one energy, like in the bottom world. This is how we characterize the transversal profile of the beamlets. This is a real image about the scan beam here that we use at the time of the commissioning. More devices that we use, like the Sphinx. It's not a list for every time for the facility, but we are showing you exactly what is my experience here. Patient-specific quality assurance. At the past, we use a set of 24 pinpoint chambers inside of the water, and then the TPS providing the plan simulated in water, and then you can measure in 3D here in small regions. This is how it looks like. Nowadays, we use independent dose calculation, which is a Monte Carlo-based model for protons, for carbon. We're working on that. And finally, a quick overview about the particle therapies around the world. So as you may see, there are 100 existing proton therapy facilities, mostly in North America, Europe, and Japan, and a bit in China, and only 60 carbon ion facilities here in the worldwide. And you might see here the number of patients treated, so we can, however, that is roughly 4,000 patients for protons, but we have roughly not even 10,000 patients with carbon. Maybe the question why is one, because there are a tiny number of facilities, only 60, and also because these machines are really, really expensive, and also because you need to convince the oncologist that this is a really nice thing to do. But there are many doubts about the radiobiology, and we need a lot of research in radiobiology in order to find which one of the radiobiological models is the best one or accurate one. Thank you for your attention. I'm sorry if I'm being late.
Muchas gracias, profesor. Muchas gracias, doctor Osorio, por su excelente presentación. Vamos a preguntar si en el público que nos acompaña hoy tienen alguna pregunta. Thank you very much, Dr. Osorio, for your presentation. If someone online have any question, please feel free to ask. ¿Alguien tiene una pregunta acá?
Thank you, Dr. Soria, for your presentation. Here is Andrea Abril. I want you to ask about the possibility to have activate parts due to the protons with the surroundings of the facility. It's possible to have it?
But so let me try to rephrase your question. So basically, the question is if there are some induced activation of the, I don't know, the robot or the some walls. So yes, of course. But the point is that basically, as the beam is, for example, this photo, basically all your beam, you are intended to stop it inside of the patient. So basically you control the energy of your beam in order to get all the high amount of energy inside of that, and then the fluence of the particles is not extremely high. So basically it's the neutrons and the fragments that you get out of the patient are really tiny. And then I cannot give you a number because I'm not in the right protection, but what the point is that yes, of course, you need to design your facility in order to have a shielding. And we have here like a concrete with some boron and no, I don't remember, it's boron. But there are some material that we have was like 1-2 meters of thickness with this called the primaries. But then usually, for example, we do PSQA, we do like 6 hours continue radiating, and you just need to, because we did some simulation about that, and you just need to wait like 5 minutes, 10 minutes before to enter to the room, because the highly activated stuff decays quickly, really quickly, and don't emit too much particles. Mostly are neutrons, but neutrons, it's not a big deal because the fluency is not super high, like it's not a collider. Let's say it's not like the CERN that you need to wait like a couple of hours before to do CMS experiment. You have a super high fluence particles colliding all the time. Here, basically, you have time. But sorry, but no, it's not activated. Let's say.
Okay, thank you.
Hi, thank you, and thanks for your talk. Very, very complete. It makes rethink everything with differently with the photons or even with protons. So how you calculate the dose, how you measure the dose, how you control the beam. I have a question related to this curve that you show us between CT Hounsfield units and stopping power. Is this stopping power parameter is the, I didn't get it correctly, sorry. Maybe it's a very basic dosimetry question, but is this stopping power really the stopping power, or has it any energy dependent? For example, if it can be used the same way in the plateau or in the Bragg peak when you calculate the dose?
No, it has a really dependency on the energy. And this is actually why we need to voxelize and try to make like a primary pre-simulation about the interaction of the beam inside of the material, because you're considering each voxel or each level of gray like a material that is given some, I mean, it's a fake stuff, but basically it's given some see here. Because look,
Yeah,
here you have,
when we use a phantom, common city phantom with different relative electron density, so you have something similar, or is the same idea, right? Or
that's the idea. When you make the commission of the CT, definitely you go in that direction. You need to use your CT phantom, but then after that you get your image in terms of, let's say, Hounsfield unit, and then you need to do something with that. And basically, this plot, this curve that is here, is showing you. Wait, try to remove this thing. So basically, it's like this. So this kind of thing, you need to put it inside your TPS. So you cannot go blindly, let's say, to you get your CT image
Yes.
and then you say, okay, that's fine, and then you start to make the calculation. No, you need to convert this Huntsville unit in relative stopping power. Each voxel represents certain amount of stopping power inside of this
So
image.
yeah. Okay. Okay, great. Thank you.
Mrs. Marsden? Okay.
Yes, yes.
Very
Well, thank you.
¿Alguien más tiene una pregunta? Or maybe online you have a question? Okay, there is no question online. Thank you very much, Dr. Osorio, for your conference.
Very good. Muchas gracias a ustedes.
Bueno, continuamos nuestras conferencias con el ingeniero Alejandro Rodríguez de Philips North Hispanic, Bimetco, Colombia, con la charla Magnetic Resonance Imaging from Radiotherapy, where MRI and CT come together. Welcome to Engineer Alejandro Rodríguez from Philips North Hispanic, Bimetco, Colombia.
Ah, no, ya estamos en el Zoom, ¿cierto? Sí. No, no creo. Ok, estamos. Buen día a todos. ¿Me escuchan bien? Buen día a todos, muchas gracias por la invitación. Me pidieron que la charla la diera en inglés, así que vamos a hacerla en inglés. Good morning, everyone who are online. Gracias. So it's an honor for me to be here in this very important event related with the experts of radiotherapy. I'm Alejandro Rodriguez. I'm in charge of the diagnostic imaging business in North Hispanic. My base is here in Colombia. And I have a lot of experience regarding the CT, MR, some X-ray. And during my work life, I had to face a lot of challenges related with radiotherapy. So I remember very well around 20 years ago when the first CT system was installed in Fundación Santa Fe and other here in Bogotá and other in Foscal in Bucaramanga, and Hospital San Ignacio also in Bogotá, and was very interesting to work with experts like you. So the idea today is to talk about from my perspective and my experience, one of the probably most interesting topics related with the workflow of the radiotherapy, and mainly radiotherapy planning. The name of the lecture is MRI for radiotherapy. So probably you are asking, why MRI for radiotherapy? MRI is a really a good modality or image modality in order to plan, to be very picky, to delimitate some lesions, some tumors, for instance. But MRI is a modality that differs from CT from his nature. How MRI can not replace, but work as CT in the radiotherapy area. So that's the reason because we called where MRI and CT come together. So
minute. No. So I want to start with with a comparison between MRI and CT. So I want to explain, probably you know, or I don't know if everybody or some of you know how was the beginning of MRI and CT. So this paper that now is in the display is probably the most important paper related with MRI. It was published in the Science magazine on 1971. And why is this paper very important? Because you can read the name, tumor detection by nuclear magnetic resonance. Was published by Raymond Damadian. Probably if you don't have access to this paper, it's very easy to find on the web. But it's very simple, but it's very interesting. Why? Because Raymond Damadian, a doctor, was very interested in a new method that in that years could help to diagnose cancer or tumors. But if you read in the name of the paper, the word imaging doesn't appear. It's only magnetic nuclear resonance. Here, some years later, very famous pictures of Raymond Damadian. Raymond Damadian is the doctor who is in the left side of this picture. And here, Minkov, one of the co-workers, were the first patient, the first patient or the first human who was a real MRI patient. So the word imaging in this case appears for the first time. This is in 1977. So what is the, or what was the initial problem? The scan time was very long, around 4 hours to take only one image. And if you analyze the resolution is not the best, but was the first step. Some years later, here, two very important scientists that work in an independent approaches. In the center, Peter Mansfield from the Nottingham University, and on the right side, Paul Latterburg, who works with universities in the New York area, were very interested in reducing the scan time. And they made the first steps to scan in only some minutes. That's the reason, because they were honored by the Nobel Prize. So Raymond Damadian was not honored by Nobel Prize, but Paul Latterburg and Peter Mansfield are, from my perspective, were the real fathers of the magnetic resonance image. Okay, so now we can go to CT. Probably this image you have shown a lot of time. This is Sir Geoffrey Hounsfield, an engineer, very important, the father of the CT. And here the Nobel Prize that was awarded to Cormac, who was working in the Cape University, and Geoffrey Hounsfield. They were working in an independent approaches also. Now, we have to talk about the image generation. In the magnetic resonance, imaging, the generation comes from, this is, of course, this is not a lecture about the basic principles, but it's important to keep in mind and to analyze how is the magnetic resonance image formed. So we have to make a lot of steps, gradients, RF pulses to the patient, receive some signals from the patient with a specific coils. These frequencies that are received from the coils are placed in this part that is called K-space. K-space is a virtual place where the different frequencies are placed, but later worked with some mathematics like Fourier transforms, and then we can get an image. So if we analyze this, if the K-space is not corrected, organized, probably the image, the result of the image at the end will have some distortions, spatial distortions. Why? Because it's not a geometrical method. Okay? What happened with CT? Oh, before I want to explain this, in this case, 3 different images from MRI. In this case, we can see, we can use a concept. The concept is weighted. This is a flare weighted imaging. This is a T2 weighted imaging, and this is T1 weighted imaging. What does it mean, weighted and T1, T2? It's a group of steps that are organized to get a different contrast. So if we can order these steps, gradient pulses, RF pulses to the patients in a specific times, we can get at the end different contrast. That is the big benefit of magnetic resonance. In the case of CT, and probably you know very well, you understand very well what is the principle. The principle is not a phenomenon as MRI. The MRI phenomenon is called, oh, sorry, it's later. It's not working. I think that I prefer with this. The phenomenon that is used for CT image generation is the attenuation, the X-ray attenuation, photons that are that interact with the matters in different ways, a Compton effect and photoelectric effect, and at the end we can get some results like the images that we are seeing in the slide. But there is a geometrical algorithm, a geometrical method. So the distortion in CT not depends of the method, depends of the, for instance, some hardening of the X-ray or some movement during the acquisition. That is the main problem that you can get with CT, but it's a perfect method, I mean CT, for identify some structure because it's a geometrical method. If the system, if the machine is working really good, you don't have problems. But in CT, it's not possible to get different contrasts as MR. Why? Because in MR, as I mentioned, we can play with the special times that we call sequence or sequences. In this case, is only one acquisition. We can play in CT with the windows. See, yes, window width and window level, but no more. In some cases, if you want to highlight some region, you have to inject contrast medium to the patient. Like in this case, for this lesion in the patient, we can depict very well the lesion using contrast enhancement, iodine, iodine injection. So what happened with the quantification? With MR, is really good to identify some tissues because the differences on tissue depends of the amount or the reaction of the molecules of water versus molecules of fat. It's very simple. But in the case of CT, it's really easy to identify the tissues using a scale, a number. This is an image of the Hounsfield scale. The scale has the name of the father of CT, and this is an advantage. So if we compare MR versus CT, CT is winning. Why? Because with every image from CT, you can depict, you can measure a tissue with an exact value. And this value comes from the Hounsfield scale. Of course, every CT image or a CT machine needs a calibration, needs a phantoms with a reference. The reference is water. That is the center of the Hounsfield unit scale. But if the calculation, if the calibration is correct, every pixel that you measure on CT will represent a X-ray attenuation. Okay, with MR is not as simple. With MR is a little challenge. Why? It's a little challenging. Why? Because depends of the sequence, depends of the times. So MR is not a quantitative modality, image modality. Okay, it's a really good image modality with different contrasts, but is not as good as CT for measure. That is one of the reasons because we use this kind of system. This is a big board. The name big board is because it has a larger board in order to have all the structures, the anatomy of the patient, a radiotherapy CT. Okay, so these systems are designed to scan a patient to in order to plan and to simulate how will be the treatment, right? Why? Because CT is a quantitative method. With MR, it's not as simple. So the first question that I want to ask is, MR as a primary imaging modality for radiotherapy? Knowing the basics, probably we can conclude, no, it's not possible. Why? Because the primary imaging modality for radiotherapy needs a quantitative image. And with MR, that is not possible for every sequence, for every image. There are different sequences, different contrasts in MR that are able to give, to get a quantification. The name of these sequences are multi-echo sequences. The multi-echo sequences is a special kind of sequences that uses different echo times, different lectures, very organized lectures in order to identify the different reactions, relaxations. But it's not the standard. So the advantages of MR, of course, we can visualize the targets and the organs that we can plan with a very with a very precise delimitation. Why? Because we can use different contrasts. That is an advantage. The second one is that is a good method, a good modality to monitoring the treatment, the response of a treatment. That is important. Not uses ionizing radiation as CT, so this is an advantage, advantage, but the density information is really important. As you see in the previous lecture that I can see, is really important to get the density information, but this is a part of CT. So continuing with the explanation, so it is possible to use two different modalities. For instance, in this case, look at this is a pelvis, this is a prostate. Look at the very well depicted parts of the anatomy, the prostate anatomy. That depict is not possible with CT. Why? Because the attenuation is very similar in every prostate, every segment of the prostate. With MR, it is possible, for instance, to depict this lesion or a lesion using a sequence called diffusion that is very important to diagnose cancers or tumors. So what is the requirement? At first, good geometrical a robust geometrical method, CT, and why not for these cases as prostate or, for instance, neck with soft tissues, MR. We can scan in a CT, then scan in an MR, and fusion the images for planning. What have happened in the recent years? The MRI for radiotherapy is growing and will still growing because the sequences are reducing the scan time. That is important. The other important thing is that the evolution of the sequences have created different methods to depict or to diagnose, for instance, pelvis or prostate, not as CT. CT has only one kind of image. So the conclusion is, and the other important thing is, MR is a expensive modality. So if you want to use MR and CT, you have to invest, or the hospital or the clinic, sorry, has to invest in an area for MR that is a complex area for the nature, and a CT area. So it's a real challenge. But there are systems, MRI systems, that have developed new solutions in order to get planning with not a standard, but a regular MR. For instance, we can use, in this case, a laser structure for isocenter. So that now is possible. We can use the same devices or very similar devices as the devices that the fixed devices that use for CT that are available for MR. The other important thing is the bore size. If you see the name of the CT radiotherapy system is big bore CT. In this case, there are big bore MR as well. Now it's very common to find systems with 70 centimeters bore size. And with 70 centimeters bore size, it is possible to use as a radiotherapy method. And the other important thing is the high gradient specifications. The gradients are the devices that we use to assign or to put the signals that were received from the coils, from the RF coils, to put in a space in three different axes. So the gradients are the main important players in order to have the best geometrical and the less geometrical distortion, to get the best geometrical acquisition and to have the less distortion. So in the latest years, we have the industry have designed different gradient methods to reduce this distortion. And we can see in this case, this is a 3T system. If you see, this is a prostate, and this is a sequence that is called diffusion. The diffusion sequence is very important because with diffusion, we can analyze, we can differentiate the motion of water molecules. And if we can check the movement of the water molecules, we can define if there are cells growing state. That means cancer or a tumor. So diffusion is a real good method. That is not possible in CT. This kind of relaxation or this kind of phenomenon is not possible to analyze with CT. So here are some examples of the methods, the devices that we use, very similar as the devices that are used for CT. So actually are the same. So this is available for this kind of systems. Of course, the table, the dedicated table, the flat table is very important because if we want to simulate, we have to guarantee the same condition as the therapy system. So it's a couch, a table that is really good for these cases. And the other important thing is that in some cases is important to move the patient, to move the patient from the table, the MR table, to the therapy area. And why not to have an MR for routine, for instance, in radiology area. And with radiology area, we don't use a flat table. We use a standard table. And with this kind of methods, it's possible to combine the two tables. And this kind of solution reduce the cost of a dedicated MR system. how can we solve the problem of the large FOV, or field of view? Because for planning or simulation is important to have all the anatomy, the patient anatomy. And with MR, is common to use or to add, to put on the patient an RF coil, a radio frequency coil. If we use a radio frequency coil on the patient, probably the anatomy will move, and that is not the idea. So this kind of systems has like this device that that are designed to reduce this kind of distortion. And of course, the laser positioning system is very similar, identical as the CT. The only important thing in these cases is that the laser positioning system for MR is different as the CT in his specifications, because the laser positioning system for MR needs or have to support a high magnetic field. So this is the thing. The other important thing that we have to keep in mind is there are some coils solution, special coil solutions dedicated for instance, in this case, neck or C-spine or brain. Because the idea, as I mentioned before, is not to move the anatomy, not to have a different correlation with the patient when the patient will transfer to the therapy system. And in this case, we can see the advantages. This is a lesion. If you see, the lesion is not clear and depicted with the T2 sequence, with this kind of contrast. With the T1 the differentiation is not the best, but appears. And if we inject a contrast, in this case, is a gadolinium, is the element that we use. We can depict very well the tumor. And look at this. This is the diffusion, the method that is used to analyze or to measure the water molecules movement, is really important to depict this kind of lesions. Here, another case. An additional point for MR is different as CT, is that we can get images in different plans. With CT, we can scan in axial plan, and then we can reformat with in a coronal or sagittal or an oblique plan. With MR, is possible to do this kind of 3D sequence as this. But if you can use a real coronal image, it's possible to get. In this case, for prostate, look at this clear image for prostate. But what is the main problem in this case? If you see, the scan time probably is higher compared with CT. So we have different challenges in order to define or to say that MRI is a radiotherapy main modality. But the next of the lecture is how can we, or how the industry is working to solve these problems. The first one, the geometry problem. We can use different methods based on calibration and some specific phantoms, and we can use specific gradients with high level specs to reduce this kind of deformation that is very common on MRI. So in these systems, we can use different geometry corrections. For instance, this is the 3D geometry correction that is available for these systems. An MRI system, a regular system that is used for radiology intentions or the radiology diagnostic, not for radiotherapy. This kind of correction is not the best, but it works for these purposes. But for radiotherapy is very important. So these systems uses this kind of correction. And for this, we have a lot of steps, like a geometrical quality process to analyze, to review daily how the system is working in order to have the spatial linearity and the amount of noise. And with this kind of measures, now it's easy to have a 3D geometry correlation. We can use a dedicated phantom also for QA evaluation. This is important for this system. This is not normal for traditional MR. This is only for this kind of systems. So the geometrical issue, the geometrical problem with this kind of methods now is possible to solve. It's important to keep in mind, of course, if the patient has some device, some anatomical problem that deflects the uniform of the magnetic fields, of course, the 3D geometrical correction will not be possible as a normal patient. So there are some restrictions. For instance, patient with some, not all, but some fiducials or some metallic implants. The second problem, the scan time. So in this case, we can see a protocol with 3 different sequences, a FLAIR, a T1 and T2 isotropics or 3D images with different contrasts around almost 18 minutes. It's a lot of time. But now using artificial intelligence in order to reduce the scan time, artificial intelligence now is available. And we have worked a lot with artificial intelligence in the industry in order to reduce the scan times. And in this case, we can reduce for the same protocol with the same image quality, same resolution, from 18 minutes to around 10 minutes. And this kind of artificial intelligence is not the latest artificial intelligence that now is available. For instance, in our case, we will launch a new artificial intelligence that can reduce this time, for instance, to a quarter. So in this case, the old sequence, or the old protocol with the 3 isotropic sequences will we'll have only 5 minutes. We'll scan for only 5 minutes. So the versatility now is available in MR. But we have additional challenges if we compare with CT. But before of the last challenge, that is the density information, I can mention, or I want to mention some additional advantages of MR for radiotherapy. In this case, for brachytherapy is really good. Why? Because we can use this kind of solution, the couch, the table that I showed, is a really good option because you can scan the patient, and then in the same tabletop you can move to the brachytherapy system, as you can see in this video. After the acquisition, the image generation, the patient is moved to the brachytherapy area. So this is good because it helps to reduce the scan and the treatment time, and of course the patient comfort. Okay, as you see, the patient is moved from the same table to the brachytherapy area. Okay, there are new solutions that combine therapy with MR. We have a collaboration with Electa. The name of this therapy system is Unity. Inside the Unity systems, they have a Philips MR system. It's the same. So with this kind of therapy, you can have the best image quality and the best therapy system. This is a really good system. But the last thing, how can we fix the main problem of the density? Because of course we have a very good delineation and accurate delineation of the anatomy with different contrasts, so it helps more than a CT. But we have the problem. This is the same of the scan time. We have the problem in the workflow, because if we use, this is CT, this is MR, important for simulation, then the images are processed, and then those calculations will be performed, and then the patient will be moved to a verification or the treatment area. So a lot of work. It is possible to use only MR for not only simulation, for delineation and dose calculation. Is this possible? The answer is yes. Now, for some cases, the method is called MRCT or MRCAT or MRCAT. What is the idea of MRCAT? It's very simple. It's to get not only the different contrast from MR, is to have Hounsfield unit as well from MR. So the real advantage of to have Hounsfield units on an MR is that you will be able to make all the calculation and the density evaluation for therapy, for simulation. So this system, the MRCAT, will generate a CT-like density information. It's a CT-like images in a DICOM CT format. So it's not a MR format, it's CT format. As you can see in this case, the patient is scanned in the MR CTA or MR CT, and the result is all different contrasts or all different weighted of MR, and additionally, the CT image is generated with a CT DICOM tag. So the CT DICOM tag images are used in the post-processing or in the calculation method that you use to have all the different information that will be helpful for not only planning, for simulation. So how it works? We can use a 3D T1 weighted M. Dixon gradient sequence. It's a little complex, but I can explain very fast. It's a T1 weighted image. It's a kind of relaxation sequence that uses a Dixon method. Dixon method is a multi-echo method. Remember that at the beginning, I mentioned that with multi-echo sequences in MR, it's possible to have quantitative images. In this case, we can use this kind of multi-echo sequence to quantify and convert in Hounsfield units. Why? Because we have references of different tissues, as well as you use in CT, because with CT, you have to, I can repeat, you have to use a phantom, a water phantom, to have the center of the Hounsfield units, that is water. In this case, we have similar phantoms for these purposes. And of course, they use artificial intelligence as well in order to have a better depict. So in this case, this kind of image that we are showing is a CT image that was generated using an MR. So is just to keep in mind, look at the geometrical accuracy, less than 1 millimeter, and less than 2 millimeter for all the sets in different axes. And the other important thing is the Hounsfield units are continuous Hounsfield units. It's not in a range. It's like a CT image. So with this slide I finished, will help to have one method, planning and simulation, with those planning with CT equivalent dose. And the values of the compared with CT is very, very similar. So this is a new design for this kind of purposes. Thank you very much. Now we have...
Muchas gracias por su conferencia, ingeniero. Vamos entonces a la sección de preguntas. ¿Alguien en el público que está con nosotros tiene alguna pregunta?
Thank you for your talk. Very broad and very good. I love this introduction of Damadi. And I have a question regarding these MRCAT images. I have a lot of questions, but you have been answering them during your talk. So, but this one. So the idea is to have to acquire in the MR and then to get Hounsfield units. I see two things that I don't completely get. So when you have your Hounsfield units, after that you go to a relative electron density step. So how is this done? And the other question is, why don't we get directly relative electron density images instead of Hounsfield unit? Because all in all, this is what we want. So why don't we create from MR images directly the images that the TPS needs? So
yes, thank you. That is an important and very interesting question. Yes, Hounsfield units as CT information is not the final the final step that you need for those planning. But is the standard. Yes, that is the answer. Is the standard. So of course we are working on electron density, but we have a real challenge with MR, because MR is based on the nucleus of the atom, and the electron density is not as easy to get directly from MR. So the best approach so far is to have a CT and use as same as CT because it's the standard. But some months ago, I have a meeting with some developers, and they mentioned the same, and they said we are working on, but the big problem, the big challenge is to become that solution as the standard. And of course, this is not a fight between CT and MR. Of course not. The idea is to get only one solution. And in the other important thing is not for all the anatomy. This is dedicated for CT, sorry, for head, for neck, and for pelvis.
Thanks very much for your talk. I was really interested in your discussion of MR imaging for brachytherapy. And I think between the step of imaging the patient and applying the treatment, you actually have to potentially change the position of the patient. For example, for gynae HDR brachytherapy or prostate brachytherapy. And a few years ago, I was talking to someone from Electa, and they were showing me very early work on designing and building an afterloader that would actually be compatible with the MR environment. And probably most of the machine, the afterloader itself, would go outside of the high field of the MR, but the transfer tubes and the catheters and the source wire and the attachment of the source and the source itself would be made MR compatible. And yes. I haven't heard anything more about this progress. Do you have any updates?
Yes, as well, good question. Yes, the thing is the compatibility of that kind of devices. Compatibility, I mean high magnetic field. But as I show in the video, the idea is to scan the patient inside the high magnetic field and then move in the same table to the brachytherapy area because of that. But sincerely, I don't have any information about the brachytherapy. It's not my area. I don't know if they are working on some kind of solutions. But I can say one thing. We are using the industry for MR some treatment methods that are compatible for a high magnetic field. It's not brachytherapy, but for instance, HIFUs, high image with high ultrasound with high magnetic field. This is a method to make some ablations, but it's different. It's not a brachytherapy. Yeah, so I think that probably if that system is very complex, I think that it's easier with the brachytherapy devices.
¿Alguna otra pregunta de nuestro público? ¿No? ¿Por acá? Aprovechen que voy bajando. Anybody who is online maybe has a question? Okay, thank you very much for your conference. Muchas gracias por su conferencia. Ahora entonces vamos a nuestro coffee break. Luego del coffee break vamos a tener la mesa redonda y a la 1 de la tarde vamos a tener un bus para las personas que van a ir al cancerológico, al Instituto Nacional de Cancerología, para que por favor a la 1, enfrente de aquí en la calle, aquí enfrente del edificio, se va a recoger a las personas, se las lleva hasta el instituto y luego de que termine la actividad los retornan aquí a la universidad. Entonces, para que tengan esa claridad. Listo. Muchas gracias. Vamos entonces al break.
Sophie Heinrich, a pioneer of flash radiotherapy in Europe and global leader in the field. These women, these two women have been much more than scientific mentor to me. They are an inspiration. Thanks to their vision and commitment, I had the opportunity to be trained in the most advanced center in the world and take part in research that is pushing the boundaries of cancer treatment. As part of my master thesis, I conducted a comprehensive characterization of 5 and 7 electron beams and 7 MeV electron beams, assessing their performance in both conventional and flash radiotherapy modality. This research presents a meaningful contribution to the advancement of knowledge in flash radiotherapy, an emerging technique that is gaining increasing attention in the field of oncology research. The goals of the research project was expand knowledge about novel dose measurement system developed for ultra-high dose rate pulse electron beams and their use in beam quality assurance protocols. The specific goals were as follows: to perform those measurements of the beam used in flash and conventional mode. To become familiar with the use of detector links to flash radiotherapy, to perform a dosimetric comparison in the quality assurance of radiation beams involved in flash and conventional radiotherapy. Flash radiotherapy is an innovative modality of ionizing radiation therapy defined by the delivery of ultra-high dose rates with a mean dose rate exceeding 40 gray per second using a linear electron accelerator. A distinct feature of this technique is that the radiation is delivered over an extremely short period of time, typically within milliseconds, which mark a significant difference from conventional radiotherapy. Preclinical studies have shown that flash radiotherapy can significantly reduce normal tissue toxicity while maintain tumor control effectiveness comparable to that of conventional approaches. This promising technique is supported by an expanding body of scientific literature highlighting its potential and its unique radiobiological mechanics. Okay. Among its technological ascents, Institute Curie features the electron flash 4000 linear accelerator, developed SIT, an Italian company leading innovate in intraoperative electron radiotherapy and flash radiotherapy since 1997. Installed at the Institute Curie in 2020 for scientific research, this accelerator is specifically designed for interdisciplinary studies in biology, chemistry, physics, with a strong focus on flash radiotherapy application. The electron flash 4000 provides 5 MeV and 7 MeV electron beats tailored for both conventional and flash irradiation. It operates operates a pulse repetition frequency between 1 and 250 Hz, delivering peak current of 108 milliamperes for 5 MeV and 120 milliamperes 7 MeV. It supports PMMI applicator region from 10 millimeters to 120 millimeters in diameter of archive ultra-high dose rate exceeding 10 to the 6 gray per seconds. The system use a standard weight accelerator structure operates um, to operate at 2.9 gigahertz in S-band in power to reson mode with ensures efficient accelerator. The biperiodic geometry alternates accelerating and coupling cells, similar to dance stacking terms, sometimes moving will other range still. Okay, electron generation is achieved through the thermionic cathode delivering up to 120 milliampere with a pulse width between 0.5 and 4 microseconds. 3.1 milliwatts. It's sorry, megawatts. S-band magnetron powers the system, protected by a circular to prevent the mesh from reflect was in the weight gain. In conventional mode, the LINAC used two inline ionization chambers for dosimetry. However, in flash mode, these chambers are automatically retracted to avoid saturation, and total beam current transformed toroids are used insert to monitor the beam current and pulse duration in real time. Okay, the flash diamond detector from PTW recently developed device especially designed for measuring ultra-high dose rate in flash dosimetry. It is made in it is made of synthetic single crystal diamond and have been optimized for ultra high dose purpose by reducing the sensitive volume and adjusting the dopamine concentration in the type later in the P type later of Stochadius. This modification result in a linear response at very high dose rate. Interestingly, the detector showed no apparent depends on dose rate or dose purpose. However, due to its recent commercial release in 2022, only a few units are currently being used in laboratories. I can perform a current measurement in both conventional and flash modes without rewiring corrections. One of its key factors is this traceability to prime standards, such as calibration with a Cobalt 60 reference bins. In addition, it offers excellent spatial resolution, enables highly precise measurements even in small files with minimal variation in absorbed dose in water. In
Sorry,
summary, excuse
Valentina.
me?
Yes, una cosa, es que nos ha tocado un poco apretar la agenda, entonces que te quedan 5 minutos de charla.
Okay. Next. A daily QA protocol is developed to ensure the stability of monitoring system of the electron flash linac in both conventional and flash irradiation mode. At 22 millimeters, a cylindrical application was attached to the accelerator jets. At the end of the applicator, in additional 10 millimeters PMMA polymetal mesaclirate PMMI plate was placed to ensure acquiring those build-ups before reaching the detectors. Okay. The variation observed in these measurements may be due to the detector instability or energy fluctuation in the beams. Moreover, it was found that intraday repeatability was better than interday reproducibility. Okay. Uh, Relative depth dose (PTD) measurement was carried out is a PMMA phantom using Gavchromics EBTXD5, which are considered dose rates independent. It depends. The goal was to investigate how PTD varies with respect to the applicator diameters, length, and pulse duration in flash mode. For each setup, two fields were placed a 4 by 4 square centimeter fields along to beam axis, c-axis, and 3 by 3 square centimeters field on the surface, perpendicular to the vent. To minimize artifacts in the build-up region. The field was irradiated with dose ranging from 10 to 50 gray using applicator of 40 millimeters and 120 millimeters and pulse duration of 4 microseconds and 1 microseconds. The fields were scanned 24 hours later using 48-bit Epson 800. The resulting dose map was analyzed using field QA Pro software applying triple channel protocols and calibration against reference dose standards. Okay. The resulting PDD cores were analyzed for electron beams of 5 MeV and 7 MeV using both 40 millimeters and 120 applicators. The dosimetry characterization in flash mode at 7 MeV yielded the following results. Okay. Which the 120 millimeters applicator and 4 microsecond pulse, the maximum dose R100 occurrence at 11.26 millimeters, R50 at 23.41 millimeters. The practical research RP was 29.52 millimeters, and the dose per pulse was 63 gray pulse. Okay. Using the same applicator with a 1 microsecond pulse, R100 was 12.50 millimeters. R50 was 24.59 millimeters. Okay, let's continue. Okay, effect of variation, the energy of the electron beams. This is figure present a comparison of the percent depth PDD cores for 5 MeV and 7 MeV electron beams using an 120 millimeters applicator and a pulse duration of 1 microsecond in flash modos. When all parameters are kept constant except for beam's energy, it's observed that the maximum dose depth as well in R90 and R50 are reached at greater depend with 7 MeV green cores compared to 5 MeV blue core. As painted, lower energy electrons have reduced penetration in tissue. For example, R90 is 17.8 millimeter for 7 MeV and 12.50 millimeter for 5 MeV. This trend is also reflected in the mean surface energy of the beams, which decreases proportionally as R50 decreases. Additionally, the practical reach also decreases with energy showing a difference of approximately 9 millimeters between 7 MeV and 5 MeV. Okay, conclusion. The following conclusion can be drawn. Measuring in conventional and flash methods highlighted that spin energy plays a crucial role in electron penetration, which is fundamental for the design of irradiation protocol in the flash modality. Some results do not allow for a strict comparison with the conventional mode due to different protocol of ways of measuring the dose in conventional and flash radiotherapy. Detailed analysis of various parameters in flash radiotherapy dosimetry provides value insights for a cure planning and affects administration of future treatment. Careful consideration of beam energy applicator signs and pulse duration emerging as crucial aspects. Okay, to conclude this deeply meaningful experience, it's like to share what truly left a mark on my heart. It wasn't only the knowledge I gathered in the labs, but the people I had the fortune to meet along the way. I was welcomed by extraordinary individuals in French, people who, without, without knowing me, opened their world to the with kindness, warmth, and genius respect. What touched me the most was that a bond we created went far beyond cultural of geographical boundaries, despite the stigma that sometimes surrounds my country. There, they choose to come to Colombia to experience my lands, my culture, my people. Um, that's just simple but powerful. Taught me that's the most meaningful science is the one boiled free human connecting through empathy and mutual respect. This experience, this just changed me as a medical physicist. It's transformed me as a person. And for that, I can only say thank you with all heart. Okay, thank you.
Muchas gracias, Valentina. Thank you very much, Valentina. Now we are going to continue with our next speaker. If you have any question, maybe at the end, you can make it for Valentina or for Sebastian. You can make any questions that you have.
Okay, good morning, everyone. Thank you for having me. As Valentina, I'm going to talk to you about my experience in the internship at Institute Curie. It's not working. Sorry. Okay, I'm going to. Yeah, okay. So as Valentina, I was there because the agreement between the National University and Paris-Saclay University through the Erasmus Plus program. This agreement was made originally with the group of particle physics from the National University, but they give us a spot for a student of medical physics, and Université Paris-Saclay have associated a lot of institutions, and one of them is the Institute Curie. Here we are, the three students that went for free from the National University. And yeah, sorry. And yes, just to talk a little about, I know that Professor Sophie have talked about it a lot, but the Institute Curie have a center of research, and in the site of Orsay, they have this team, and in this team they work in these research areas. But for us, in medical physics, the research area of interest is the new approaches in radiotherapy, which include the electron beams flash radiotherapy. Sorry, I copied. Okay, so what I did, I summarized in this very long title, and it was the beam and detector characterization of diamond detectors and ultra-thin ionization chambers for the development of dosimetric protocols in preclinical studies in flash radiotherapy. And it was a work that tried to take the detectors that has been already developed for flash radiotherapy and try to develop the protocols for the kind of treatments that they made in this laboratory. So first, I going to remember again why the conventional detectors are not suitable for flash radiotherapy. And this is because, okay, first, with the gold standard for dosimetry in this case, for radiotherapy in general, are the ionization chambers. So all the protocols, for example, TRS 398, are based on ion chambers. But what if we lost our gold standard? And in this case, for flash radiotherapy, we lost this gold standard because as we are irradiating with very high dose per pulse or very high dose rates, we are generating a great number of ions in a very short time. So the density, it's very high. So as the density of ions is very high, the probability of recombination is very high too. So, and plus, as we generate a very high amount of charge, it perturbs the electric field inside the ionization chamber. So if we combine both, at the end, we obtain a very high ion ring combination. So this is a problem with these chambers. And that's why the physicists had to develop a new kind of dosimetry from the scratch, starting from the passive detectors. But you know that passive detectors, okay, have the advantage that are dose rate independent, but it have a delay to obtain the reading of the detectors. So it was better to, okay, we can use it as a reference, but it's better to develop real-time detectors. So the strategy was first to adapt dot. I'm going to talk about the both detectors that I wish I work. And the first was the diamond detector that was characterized by these authors, including Professor Spee. And this detector was optimized to be used in flash radiotherapy. And it was tested, it was already tested. So it actually, it works very well for flash radiotherapy. But as we would like to have again, our gold standard, some authors have worked in the development of ultra-thin ionization chamber. And some of the physicists that works a lot, that have worked about it are Faustino Gomez and Araceli Gagos. That I was lucky because they was there in the Institute Curie when I went. So we was able to use one of their prototypes and the water tank. So it was a very great advantage. And just a summary, the way they optimized the flash diamond was changing the size of the diamond. Here you can see that conventional diamond saturate, but if we decrease the size, we improve its response and changing the doping. So that's what the strategy for flash diamond. And for ultra-thin ionization chamber, the strategy was to decrease the spacing. They use plane parallel ionization chamber. So if we decrease the spacing between the electrodes, we improve the ion collection efficiency. And also, if we use it in a high voltage, in a suitable high voltage, not too high because we have the charge multiplication. But that was the strategy, and we use this prototype that the spacing between the electrodes was 0.25 millimeters. And what we did first was the beam characterization. It was performed with radiochromic films to measure the PDDs at 7 and 5 MeV, and to conventional and flash. After that, we also characterize the beam with the profiles, and we use that after to characterize to the detectors. And also, I have to mention it before. I was working with a doctoral student at the same time. So some of these characterizations was used for both. She used this information to perform Monte Carlo simulations. So we would like to characterize all what we were able to characterize, to have a very good characterization of the beam for the simulations. So one of that characterization was to see what was the divergence of the beam without the applicator and with the applicator, and you can see how we improve the uniformity when we use applicators and all that kind of characterization of the beams. Then, as a way to characterize or to know if to test if the detectors that we was testing was suitable for flash radiotherapy, was to compare the PDD measured with it, because the PDD is a characteristic of the beam by itself. It don't have to change if we change the detector. So if it changed with the detector, maybe the detector, this is a signal that the detector could be suitable for this. So this is one example. We have a lot of data and without process. But this is one example of the kind of characterization that we did, and it shows, in principle, a very good response, a very good consistency between the films, the ultra-thin ionization chamber, and the flash diamonds. And another very important part was that, okay, we have the flash diamond has been already tested and it works very well. But the ionization chamber is still being testing, so there are some things that have to be researched before to know if actually are the best detectors for be using here. And one of that is, if you remember the formalins for dosimetry, we have this expression. So for this chamber, where we have the charge measured by the chamber, the calibration coefficient, the coefficient that related with the quality of the beam, the pressure and temperature correction factor, and this was the most important for us, the saturation factor and the polarity factor. The saturation factor is very important because if you remember for the conventional protocols, when we want to calculate the saturation coefficient, we measure at 2 different voltage, and then we apply a polynomial and find the coefficient. But this is based on some approximations that for this kind of beams are not suitable. So this coefficient has been already tested by Faustino et al. But still, it is very interesting to see how it changed. That is related with the ion recombination, the saturation factor. And the polarity factor is very important to see if, as you remember in this kind of beams, for us it's very important the pulse by itself, study the beam pulse by pulse. So for us, it's very important to see the dose per pulse. And sometimes the response of the detectors could depend on the dose per pulse. So we would like to check if these parameters change as we change the dose per pulse. Faustino et al. Have tested already if the polarity coefficient change with the dose per pulse, but in a very restricted range of dose per pulse, between 0 and 0.5 grays per pulse. So what we wanted to do was to explore this coefficient in a wider range, up to 8 grays per pulse. And we use it. All these kind of measurements was performed with the diamond, using as the reference the diamond detector. And yes, this one was of the. This is an illustration of why the conventional ionization chambers don't works. In this case, I compared the Marcus chamber, and we plot the change per pulse as the change per pulse collected by the ionization chamber as a function of the dose per pulse. And as you can see here, the Marcus chamber have a saturation, so that's why it's not suitable for this kind of flash. As we increase the dose per pulse, while for the ultra thin ionization chamber, we're still keeping the linear response. So this is an illustration of why we need to adapt this ionization chamber. And here you can see, this is the plot of the charge or the signal as a function of the voltage. Just as you remember, when we studied the ionization chambers, we have different regions. We have the recombination region, then we have the saturation region where the ionization chamber works. Then we have the proportional counting. So in this case, we plot that in a restricted voltage because we was able just to from 50 to 400. But it's really interesting to see how, as you can see here, for low dose per pulse, we meet the saturation in 100 volts. So we have the saturation, it works very well. But as we increase the dose per pulse, the saturation, we meet the saturation in very high voltage. So this is related with the charge collection efficiency. And we already know that as we increase the dose per pulse, we lost charge collection efficiency, and we can check it here in this kind of plot. It's very illustrative. And as a note, as a reflection, sometimes when we read some papers about flash radiotherapy dosimetry, we always see that they say that the ionization chambers have saturation, but they don't specify what kind of saturation, because here that's the saturation that we don't want. Yes. But this saturation, we want that we're saturated in this region. So sometimes it's not clear what saturation they are talking. So Professor, I'm agree with Professor Sophie when we say that maybe it's better to use the term that say that we have a very high ion recombination rate instead of say that we have saturation, because it's not clear. Yes, another things that we do for characterization of the beam was to study the beam at different field size, because as you know, for preclinical applications, we would like to, or the researchers would like to radiate, for example, mice, and there are very small structures. So we explore how it changed the beam in that conditions for different field size. Also, it was a really good experience in the design of experimental setup because in the clinical in the clinics almost everything is done, so we don't care for things that are actually that we have to care. So in this case, what is the best reference, how to use our reference detector, because here here we don't have a monitor chamber as a conventional beams. So it was a very good experience. And for example, how to work if we radiate with very high dose per pulse, and we use a window of PMMA, the PMMA start to damage with the radiation because we radiate with very high doses. So how to work with that, it was a really good experience. How to measure the build-up region, because it was really tricky. If we measure it with a flash diamond and then we measure it with two different ways with the, for example, with the films, it's different for all. So it's really, really tricky, and it was really funny to think about the experimental setup. I also have the opportunity to learn about how to use Faraday cups as dosimeters. It was very interesting because it was the first time I used it, so it was very interesting. And it was really really interesting too how to monitor these beams, because again the how we monitor the beams in conventional, we use ionization chambers too. So as the ionization chambers are not suitable here, they used a current transformer, and here we can check pulse by pulse how is the behavior of the beam. So it's really interesting to see that kind that we don't care in the conventional because we already have the monitor units. But here is really interesting how to monitor these beams. And yes, for a future, what the final objective was to develop the protocols, the symmetric protocols for the preclinical studies, and did implies that we would like to calculate the dose, the actual dose that are delivering, for example, to the lung. And for that, we are working together with Angela to do some Monte Carlo simulations. Here you can see some of the setup of in the simulation, where we have the applicator, the collimator, and my support that was the segmentation of the phantom. And we are still working on, for example, if we would like to create physical phantoms, if we have to consider the bounds of if it don't change too much the dose, for example, we would like to explore all that kind of things. And another kind of experience, I have the opportunity to visit the proton therapy center at Institute Curie. And also, no, it was not just an academic part. There was some funny parts. Curie Institute have an association of students that organize some meetings where you can meet some other people, some other biologists, some other medical physics, where I have the chance to talk about with some doctoral students from the proton therapy center or the project of the very high energy electrons. Some meetings doing by the team laboratory, and of course all the places that you can visit as you are there. So thank you very much for all the guys that was there. They gave me a very kind welcome, and especially for Professor Sophie, and for my lab mate Angela, who support me a lot in my experiments. And that will be all. Thank you.
Thank you very much, Sebastian, for your share your experience at the Saint-Clair in Paris Saint-Clair. Someone has maybe a question, maybe online. We have any question? Aquí tienen alguna pregunta? Here, someone has a question.
The questions can be very broad about the exchange, not only
yes,
you can,
not
only as a scientific curriculum or something like this. So, y en español también, claro. Hablo en español, no sé.
Sí, sí.
Un poquito
Sí, hablo un poquito. también si tienen preguntas para Valentina.
Okay, thank you for the talk. Very interesting. I guess maybe it's a bit of a broad question, but I wanted to ask you if you have any advice for someone who wants to maybe do the same thing, go to an exchange. Quiero preguntarte si de pronto tienes algún consejo para alguien que quiera ir en un intercambio, pues académico como el que tú experimentaste.
Sí, pues I'm going, well, okay. I'm going to ask, I'm going to reply in both. First, I was looking because the agreement was already done between the universities, so I just have to apply. I have to do an interview with Sophia, and she chose me. So it was easy for us. Unfortunately, the agreement end this year, unfortunately, so they have to do it again. So that, as it was very straightforward for me, I don't have a really advice, but yes, so sorry. So that's why I don't have a very good answer for that.
¿Quieres que le preguntemos lo mismo a Valentina? Valentina, con relación a la pregunta, ¿podrías darnos tu opinión? ¿Qué recomendaciones das a las personas que quieren hacer esta misma experiencia?
Bueno, las preguntas sí las voy a contestar en español. No, pues primero que nada, el inglés creo que es fundamental. O sea, creo que es como la parte más importante. Pues desafortunadamente, cuando...
Yo te interpreto, Valentina. Me vas contando y yo te voy traduciendo al inglés para las personas que están conectadas, ¿vale?
Ok, perfecto. Entonces, fundamental tener un nivel de inglés medio alto.
Okay, Valentina says that some tips that she can give is the first of all, have a very good level of English.
Sí, también pues como ir a la par, bueno, en cuanto ya a la experiencia ya, me servía muchísimo ir leyendo lo que la profesora Sofía recomendaba, o sea, ir como estudiando después de las asesorías que ella nos daba en el laboratorio.
Okay, when she has some meetings and accessories with Professor Sophie, she has to review and to study the topic. So this is so important in order to learn.
Y tercero, si pueden también como anticiparse a conseguir su hogar allá en Francia, es decir, o sea, encontrar su hospedaje fijo también es súper importante y por supuesto llevar muchas ganas de aprender.
Okay. The third thing that Valentina says is that it's so important in advance to look for a place to live and be with all the attitude to learn.
I would like to add something. If you are going to do an internship like that, where you are going to be in Europe like less than 3 months, it's more difficult to find a place because you don't have a visa. You can go to the European Union without a visa, but that's a problem because the locations ask you for a visa. So have it in mind if sometimes you are going to do that.
Thank you very much. Muchas gracias. Dr. Sophie.
Thank you. And just to add something about the language, because of course this is very important. And as Valentina said, it's important to be able to interact in English. But if you go, at least in France, you should also investigate a bit if the lab is used to interact in English. Because in our lab, there is a lot of international students, so we talk English all the time. We do the lab meeting in English, whatever. But it's not necessarily the case. And of course, we don't expect you to speak French. But yeah, it's better to choose a lab which is able also to speak English, in addition to you being able to speak English.
Thank you very much. ¿Alguna otra pregunta? Some questions online.
para añadir, sí, el convenio está acabando ahora y esperamos renovarlo, ¿verdad? Eso. Pero, pues, de todas formas, las puertas siguen abiertas para ver otras opciones legales de colaboraciones y todo eso. And in English, so the agreement, yes, it's ending now, but we are going to renovate it. So no worries, we will find out a way to be there in a legal way. I mean, not with a tourist visa, but with a student visa, something like this.
Continuamos entonces con la siguiente conferencia. Le damos la bienvenida al estudiante de doctorado Ian Rossi de la Universidad Nacional de Colombia. Él nos va a hablar sobre los avances en detectores de semiconducción para radiación ionizante. Now we have the doctoral student Ian Rossi from the National University of Colombia. He is going to talk us about advances in semiconductor detectors for ionizing radiation. Welcome, Dr. Ian. Bienvenido, doctor Ian. La única recomendación es que estamos un poco apretados en la agenda, entonces por favor le recomendamos de pronto acortar un poco su charla. Muchas gracias. Thank you very much.
Thank you so much, Dr. Bichit. Maybe we can check if you see my presentation. ¿Me puede confirmar que me están escuchando y viendo la presentación, por favor? No hay nadie.
Sí, se está viendo la presentación y se escucha bien. De pronto te acercas un poquito más al micrófono porque siento que está un poquito bajo, pero nada más, está bien.
Okay, thank you so much. Hello everyone, my name is Ian Rossi. I'm going to show you something about the advance of semiconductor detection for ionizing radiation. And I think I like it to start with this video. That's so interesting because this is a huge application about these new technologies we see. So I'm gonna show like 30 seconds. No, sorry. Sorry. Okay, I'm gonna, let's deposit. So I like to present this image. It's particularly compelling because it transforms an invisible phenomenon like radiation into a reference visual representation. So like why we use what we see here is like an application of the new detections equipment that advanced country has. So using a drone mounted in gamma spectrometry, it's possible map radiation levels in a complex terrain with a high spatial resolution. What I mean is we can see like that anybody can see in this image. So it's so important that we know there is a lot of another application in the new technologies, and they are very important to the security and the sorry. So I like to ask some questions. You know, required to answer them out loud. There are questions for you. Think about personally, honestly, and call me. There are right, no wrong answer. I simply invite you to reflect on your experience, your country, your environment, and your reality. Do you know that today it's possible to visualize the radiation on a map using drone and advanced sensors? How do you important to you is think about the see the radiation, something invisible in real time over affected area? What role could this technology play in a public education about the radiological risk? What political advantage would there be in knowing in detail the state of nuclear development in other countries? So, how do you see this project an innovation solution for the monitoring of uranium contaminated sites in remote areas? It uses a drone that has a 25 kilograms, equivalent with a cesium and a gamma spectrometer of yoduro sodium, allowing accurate radiological maps to be obtained without the need of helicopter or other flights or road works to take that image. The system was tested at nuclear legacy sites in Kazakhstan, and they had a good resolution for isotopes like uranium-238 and potassium-40. And that data was consistent with the ground-based measurements. So, in this presentation, I like you show you just six steps to take in this moment. So the semiconductors enable the development of detection technologies based in mechanisms such as ionizing radiation and optical or electrical mechanisms. We see that so far the thermal detectors, that is an indirect measurement, and optical stimulated luminescence, like a OSL detectors, that they are so indirect measurement. And we have radio luminescence and scintillators detectors that they are same indirect measurement. We see later what this part about the indirect measurements. And we have a wide band gap solid state detectors, like a silicon carbide polytype, like a gallium nitride and oxide gallium. And there is a new application, okay? So let's go back to the beginning to see a little physical aspects that is so important to understand this concept. So, we have this is the most easy way to understand how works these semiconductors. Where in the left part we have the insulators. They have a completely valence band and completely empty conduction band. There is a large energy gap. That is the energy that I need to take an electron for the valence band and take it to the conduction band. And so maybe it's like a 5 or more electron volts. The electrons cannot easily cross into the conduction band, and they not conduct electricity in the case of the isla in the insulators. So if we see in the middle, we have the semiconductors. You see that there is let me check right here. This is the band energy, like I talked before. In the insulators, we have a wide energy band. So we need more energy to take one electron from here to this to move right here and have conduction. So this is so difficult. Also, what I need, this is where I need so much energy to take that. In the semiconductors, they also fill the valence band in empty conduction band, but they have a small energy gap, like a 1 and 4 electron volts energy. And this is when I have the energy to take one electron here and go and take that and send to the valence and the conduction band. We have a response. And that is more important because in the semiconductors, if I have another materials in dopage, in making doping in these materials, we have another levels in the energy band in the middle in the band gap, and this is where I can change that energy band. So we need less energy or more energy to take that electrons and move about the move in the conduction band. And the last one in the right are the metals and are the sorry are the conductors. Like there is an band gap in the conduction band, particularly that you have this space. So the conduction band and the valence band are in the same space and the same volume, and they are the electrons move freely and very and even at a low energies. There is an excellent conduction electrical, but no like a semiconductors. Okay, we will see later this part. Okay, I think we needed understand there is a two mechanisms or categories for the really what I am measuring. What is the property that I see with my equipment? So in the semiconductor detectors, the measuring performed is indirect since ionized radiation is not detected directly, but rather the effects it produces when interacting with the material. There are two main mechanisms. The first is based on the emission of the photons, like you see in this image, resulting from the thermal, optical, and the case maybe the technology. If you see the technology, that is where how I take that electrons of the material and have a signal. The first is based on the emission of photons resulting from the thermal, optical, or ionization excitation process, as occurring in thermoluminescent OSL and scintillators detectors. In this case, the signal generated is a luminous and requires external system for reading. What you see, if I have a photon for my materials, after that emission, I need a equipment that take that photo and convert that signal in electric signal, because I don't see or I don't have the equipment adequate to take this photo. Okay. In the in the case of the solid state detectors, the mechanism characterized is based in the creation of electron hole pair with the semiconductor. What I say, when I have a radiation unit in our material, in our semiconductor, we have electron hole pairs that move with an electric field. That electrons move to the one material, to the upper material, and the holes, well, in this case, the holes move up and the electrons move down. And we have the signal and take the signal and convert that emission in an electric signal, and that is where I can check my measurement. Okay. Let me check. Okay. So if we see our equipments really take another measurements of what I can, like I think. Many times when you see a multimeter, like another example, of any measurements or instrument, we assume that the value displayed on the screen is something that the device reads directly. However, this isn't entirely true. In reality, many of the variables we measure, such as a current, resistance, or capacitance, are obtained indirectly. What the instrument does is internally apply a no signal. For example, if we have a current or voltage, the measure of the response of the component is under test. From that response, and using a physical laws such like Ohm's law, or capacitance discharge or Shannon equations, the multimeter calculates the desired value. In the other words, it doesn't directly measure what we want, but rather infers from other more accessible measurements. Okay. This is so important because we don't know really what I am reading in my equipment. Okay, if we see the technology of thermoluminescent detectors operate through an indirect measurement, like I said before, is a process based on the temporary storage of energy caused by ionizing radiation, like you see here. I have ionizing radiation right here. We have a creation electron pair, like I see in the semiconductors, but we don't have an electrical signal from these electrons, or we have a photon signal, and we take it with a photon multiplier to take a signal really. So when the LED material is exposed to radiation, the electron receives enough energy to jump from this valence band to the conduction band. Some of these electrons no return immediately levels and they remain trapped intermediate levels, like at this one in the middle. And these in these middle levels generated by impurities or crystal defects that has my material. This energy remains stably stored. I have information stored in these materials until the material until the material is heated in the reader. In this case, I have a thermal emission and thermal excitation. So when I have this effect, the electrons that drop and remain in these middle levels take at the valence conduction, and they a little time, like nanoseconds, they down or they fall to the levels so closely to the valence band, and they recombination and generates a photon. This energization, this falling of the electrons and recombination, they create a photon that I needed to take in another equipment to take that signal. Okay, the light is detected and quantified, and this intensity is proportional to the absorbed radiation dose. Thus, the LED doesn't directly measure the radiation, but these are affected on the material through the cell release signal light. Okay. They had a high sensitivity and contemporary stability, and compact size and reusable, and delay reading allowed the dose accumulation. A disadvantage, the structured reading, what they say is when I take the information of what is the energy that my detector has, then I don't make this, I can't take this information later. So I just have one opportunity to take that information, okay? And we have a big problem that's not offered to real-time reading, because I need a big equipment or like a photomultiplier to take the signal, okay? In the case of the optically stimulated luminescent detector radiation, it's measured also like measuring indirect. The measurement based on the effects that radiation induces in these materials. So we have the same process that in this case I had radiation ionization on my material. You created electron pair holes to the material, and after I need a stimulation to take the electrons that are remaining these traps or middle levels, to take that electrons and the valence conduits for later have a combination process to take that photon. And when I take that photon, I needed again a photomultiplier to take that signal and sorry, and the signal allowing the observed radiation to be quantified without destroying the information on a single reader. This is a good advantage that I have with the OSL detector, because I think we can measure but so many times that we want, so that doesn't happen in the TLD detectors. Okay. There is a same process in the case of TLD. The just difference is the stimulation. We have thermal stimulation in the before process, and here we have optical stimulation. Okay. and the radioluminescence and scintillator detectors, we have the same process. We have radiation ionization, creation of electron pair, electron hole pairs, and then later we have the levels in the middle of the gap of material, like a traps. They just remain my electrons, or maybe my holes if their levels are so closely to the valence band. And later we have a stimulation again. Okay, in the case of the radioluminescence or detector scintillator, we have this response immediately when I have the radiation. So we have the radiation, and the same radiation take this signal, and like this process take like a nanoseconds, that 10 to the 8 minus 8. So we have here the signal, the photon signal, and I needed again a photon multiplier to take the signal. So if we go come back to this part, we see the intermeasurement mechanism on these four technologies really, is the emission of photons emitted under a process of thermal, optical, or ionization excitation. And we need a photon multiplier to take that photon and take that signal in the current signal. In the case of the solid state detectors, we have the creation of electron hole pair, like a same. This is the same mechanism that we have here. So they in this case we don't need the electron hole recombinate. So we needed is take that signal, take that electron, take that hole, and take the move out of my material and take that signal. So we have here a current for the creation of electron hole, and we have the emission of the photons of the creation and on process recombination of the electron hole pair. Okay, that's so important to take in this case. So in the case of the semiconductor detector, we have the levels in their middle gap. They are so important because the detectors operate under an interrelation, like we said before, that is based on the iteration of the radiation with the material. When the ionization particle of photon pass through the semiconductor, this one transfer its energy to the semiconductor or to the material. Under an intermeasurement principle based in the interaction of radiation with the material, crystalline structure, when an ionizing particle pass through the semiconductor, is transferred its energy to the material electrons, generating my whole electron pairs. So this carries as separate and get by applied an electric field, like we see before in the before image. These carriers are separated and geared by an amplified electric field, producing an electric current proportional to the energy deposited in my material. The resulting signal is amplified and analyzed to determine the type, quantity, and energy of the radiation. Although a directed electrical signal is measured, the process is still considered indirected, since what is detected is not the radiation itself, but is the ionizing effect on the semiconductor. This type of detector is well used in a spectroscopy, like we see in the drone image we have in the first presentation. It's well it's used in medical imaging, tomography, environment monitoring, and portable design of the material. The generation of electron hole pairs are separated and geared by the electric field. And that is so important because this signal is that we have to take the signal and so we have a relation between that current and the energy or radiation ionization that the material has exposed. How the advantage in these materials is a high energy resolution, a fast response in real time, because this process is so fast, like in nanoseconds, I say before. And so many any technologies, we have a low voltage operation in when don't need external amplification, but another another equipment required really high voltage. And in the case of the detector of German, requiring cryogenic cooling, like a liquid littering to works, because they have a low high voltage. And this one, okay, and this one had. Okay, well, I'm gonna so only fast. We have technology solid-state detectors of of SiC. In this case, we have layers of semiconductor materials, and the contact is sharply contact and non contact to take the signal. And this is the creation of electron pairs. Here we can see the cones per channel in another temperatures, like the response of the raw material, like between 200 Kelvin and 300 and 390 Kelvin. This is so similar in our case. There is so important in aspects like
well, Ian, you have 1 minute left.
Oh, okay. I'm going very fast. Later, this one I like to show you. This is a detectors of gallium. We have this image show us like a response in the another voltage, and this one is so nice because we have needed like a 600 volts to get the better signal. And to terminate, to finally this presentation, I'd like to show you another system that uses a particle detector. There's this one. We use semiconductor detectors, and it's using a HoloLens to glasses. The goal is providing real-time visualization of irradiation or expulsion areas, superimposing measured data directly into the physical environment. The process begins with a detection based on Cesium or ST-Veil, capable of discriminate between the gamma particles and neutron. And this is the video we see in the first one. So this is I am finished here. I don't know if anyone. This is the works that I take the information, and I think the time is over. Thank you so much for everyone.
Muchas gracias. Thank you very much. ¿Alguien tiene una pregunta aquí en el auditorio? Someone has a question? Are you sure? ¿Tenemos alguna pregunta? Ok, ¿nadie? ¿No? ¿Preguntas? Bueno, muchas gracias por su participación. Muchas gracias por la conferencia. Thank you very much for the conference and for your participation. Ahora para recordarles, a la 1 vamos a tener un bus que nos va a recoger a las personas que van a ir al Instituto Nacional de Cancerología al taller de braquiterapia. El bus va a estar aquí por el anillo vial enfrente de este edificio a la 1 de la tarde. Bueno, por favor, las personas que van están seguras de que les llegó el correo de confirmación de que fueron seleccionadas para ir al Instituto Nacional, porque pues la entrada es restringida y si no lo tienen, pues probablemente no los dejen ingresar. For people who's going to the National Institute of Cancerology, there's going to be a bus that is going to take those people to the institute. So please be at 1 in front of this building by the circular street of the university. Las personas que llegan por su propia cuenta al instituto Van a llegar a las 2 de la tarde, antes de las 2 de la tarde para poder garantizar el ingreso. ¿Por qué puerta?